Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about upgrading India's grid for renewable energy. So let's dive deep into it. So what exactly is the problem? Well, problem is that without proper grid, let's say, yes, grid is a thing, it's an entity, it has its own logic, so to say. If it's not properly aligned for renewable, yeah, you cannot integrate renewable safely. You can add little bit, that's not an issue. But the moment percentage starts to touch double digit, meaning 10%, 30%, God forbid 50%, then you are in dangerous territory. You are no longer safe. What does safe mean? Well, safe simply means adding intermittent generation can make your grid vulnerable and fragile, meaning you can have one thing going off and that could trigger what we call cascade failure, meaning one thing happened, led to another thing, and voila, the whole Texas is out of power. Or again, you can have like one thing happened, led to another thing, poof, whole UK and all that is poofed. And again, same thing can happen in Australia, 28 September 2016. Wind blew over some power cables, poof, half of Australia, poof. Now, again, it's not half, but you get the point. Like, there is a vulnerability to our power grid because it was not designed for intermittent power source. If we do not reinforce it, if we do not adjust it for intermittent power source, yeah, we are vulnerable. And there are consequences to it, meaning if a government, let's say Indian government, is like, we want more solar, we're going to give incentive to solar, that's good, that's GG. But if they do not plan it adequately, it could lead to a serious failure where you will lose ROI, and that's the most critical aspect. Nuclear does not work because it does not have ROI. Any government, hundreds of government have tried. Yes, there are 150 countries, actually more than that, around 200, and more than enough countries have tried with nuclear. Outcome is always the same, be it France, be it Germany. It's like everything works, it's just that until you have to pay for it. So only two people like nuclear, scientists and engineers, and only one person who hates it, the people who have to pay for it. So it's like, oh, America has cheap power. No, it has power purchase agreement. That's why the power is cheap. Power is not actually the cheap. Basically, it's like instead of going like this, you have to going like this. So money has to come from somewhere. Oh, the power plant operator went bankrupt. Now government has to bail out. It's your money. It's just like, but on your electric bill, it's cheap. So that's why you want ROI. Solar has very good ROI, but if we do not plan the grid, it would reach a point where solar is just shutting itself off. So forget your ROI. You will not have return on investment. It's like, yeah, back in the days, in the golden period, we used to return our basically investment return happened in 5 years. 8 year was like, really bad, but like now it takes 15, 16 years. And even then, it does not happen. So that's a very serious thing. You want organic momentum of renewable energy to drive it. Then it will automatically happen. Failure to do so, you will literally reach a point where it's like, we are forcing government, people to do that, and people are like, hey, why our cost of living is going up? You never want to lose a return on investment. That should always be there. We built a wind farm, now we are GG. We are making money. That should be the natural progression. It should not be like, we are subsidizing, you are building it, but there is still no ROI. That means you have to pay more. And that again, people will hate it. And again, mismanagement led to all of these things. And that has serious consequences. Because, for example, this Texas was the most hilarious example simply because is the gas power plant or coal power plant that malfunctioned, and somebody committed as like wind turbine went offline, which was true, but it went offline because coal and gas malfunctioned. And somehow somebody shared a photo of a European frozen over wind turbine, and it's like Texas winter and wind turbine. Everybody ran with it. People started hating renewables. Same happened in 2016. There was a lot of hatred towards renewables. It's like, renewable is giving us such a weak power grid and all that. And I do not blame people who start to hate it, because again, if you are living in a country like people who are living in Texas, they were like, hey, for last 400 to 600 days, we never had a power cut, to having a power cut in such a crucial moment where it's like people are actually freezing. It was bad. And again, even in UK scenario where things were bad. So I can understand the hate, and you have to understand, because the grid was the weak link, not the renewable energy, not the customer. It's the grid that was the failure point. So this is the real problem, and it can get out of hand. These things are localized event. You could have a whole country failure if we do not plan accordingly. So what's the first defense? First defense is interconnects. Now this is an old Indian map of India's HVDC interconnect. India and China is really world leader in high voltage direct current interconnects. And you can see India is divided in a few segments. You have north segment, west segment, south segment, east segment, northeast segment. And India is the world's first country to have multi-junction interconnects, meaning we have East Agra corridor. That is from basically north east and northeast. Now that is connecting some hydropower in the northeast, some power loads in east and some in Agra. So benefit is this, generally you have HVDC, that is like a Three Gorges Dam to a substation. That's it, A to B. Now what India has is A, B, C, meaning we can balance load. That's a next stage evolution. We have reached that few years ago, and that is around 8 gigawatt in capacity. So big puppy. And again, you can see there is another connecting north to west, another, because again, west is kind of huge. So you have another west to west, another south to east, these sort of interconnects we have. Yeah, this is not enough. Now, to be fair, this is old map, 2018, but we need exponentially more than that. If we do not have that, we again go back to the same issue that California is facing, Texas is facing. So things are bad. Basically, grid is built on a core logic. How did people build grids hundreds of years ago? We were following the same philosophy. It was this: there is a power plant, you distribute energy, go home, done. However, renewable does not work that. Renewable is a mix between this. Basically, you have decentralized into localized, meaning it's complicated, so to say, because you can still have like how we used to have is like, okay, we're gonna have a big ass coal power plant that is like 1.6 gigawatt. Oh yeah, so we still have that. It's just that now we have this 2 gigawatt solar farm. India has that. Awesome. But here's the deal: where is that solar farm? Back in the day, you had to balance everything out, because again, you can plant coal power plant anywhere as long as you can have a railway line, as long as you have a water body, and railway line, water body, and station connection, grid connection, so to say. So if you had all these three things, bam, power plant. Solar does not work that way. Solar is like, bro, I'm rich here. Basically here, you have to put solar farm there. You do not put here, even though load is here. You have to put it there. So you see, we went from like, this is a box, you put it, it's like, now the box decide where it has to be. So fundamentally, this has a random location from an energy point of view. Again, from a natural point of view, nature is like, lot of heat, put solar here. Lot of wind, put wind here. You get the point of it. So again, we have to follow nature. So from a power point of view, it looks random. It's like, why do you have a solar farm here? Why you have a wind farm middle of nowhere or actually on top of a mountain? You see, that's the paradox. And where does this come from? This comes from rooftop solar. Rooftop solar was not a big deal. Nobody was thinking about it until people realized how many people were starting to install it. So we actually have few gigawatts. Let that be very clear. Gigawatts of rooftop solar. I'm not talking solar farm, rooftop solar. Like my rooftop has like 2 kilowatt. Again, it's not a grid connected system, but many people have grid connected system. Now, is that a big deal? One? No. One home? No. One block? No. 10 block? Oh yeah. Hundreds of blocks? Yeah, that's a big deal. Now you literally have a random system where you cannot control it. You can disconnect a solar farm, but you cannot disconnect someone's house. Because again, it's using the same cable. It's not like input cable is different, output is different. You cannot disconnect it. You see, now we literally reach at a random point where it's like, oh sir, that let's say hospital, a lot of Indian hospitals are huge structures. So they have like a lot of power, 500 kilowatt power. Let's say that 500 kilowatt surplus happened. Then what? You can't take a phone call and connect to the inverter that is in the hospital, shut it off. That's not allowed. So what you have to do, you have to cut power from somewhere else. So you see, like this structure is gone. This structure is gone. We have basically hybrid between this and this. So this decentralization and random location creates a hassle. We did not design the grid for that. All these things you see is like designed for, this is where we have our biggest substation. We're going to point it that there. We need a hydro dam connected there. We're going to put it there. So we have changed fundamentally. So what do we need to do? Well, grid needs to scale in capacity and reach to not become the bottleneck. Right now, that's the bottleneck. And again, the same happens in America, same happens in Germany. Germany is ironic. Half of the country, GG, renewables, no problem, shut up, take money, go home, have fun. Other half, yeah, we barely have power, we have to buy power from other countries. Because they do not have interconnect from in themselves, like exactly like how India, we have few, they need far more than that. And again, we also need far more than this. We need almost like a loop. We need a few loops of HVDC interconnects where we are like pumping gigawatts, at least 10 gigawatts everywhere, here to there, here to there. So it's like, oh, power is produced here, got this. Overproduction here, got this, take this. That's what we need. Failure to do so limits large-scale renewables. And without large-scale renewable, rooftop solar, cool and all, it does not have enough oomph to drive industry. So that's why we really need interconnect. And that interconnects also gives you redundancy. In case of fault or failure, you no longer go poof. You're like, I got this. Like again, these interconnects, that's the primary function. It's like, okay, if the coal power plants are reaching saturation, or most likely what happens is like, hey, we need to shut it down for maintenance. Okay, now you talk to someone else, power dispatcher. So it's like, hey, we need this much extra capacity from you. You talk from someone else. You have some backup. You have some spare. That's how we do it. And again, wind and solar requires a bit more flexibility on our end. So interconnects needs to improve drastically. Basically, think in this way: we are running at a 2G network. We need 4G network for HVDC. Now that solves interconnect. That solves in the moment problem where it's like, oh, too much production, we got this, we can distribute it. But it will still lead to a one point where you have still curtailment. So we need energy storage. So why do we need storage? Why can't we just solve it? You can technically solve if you are in European Union, because they do have the luxury of such a large land mass that they can have like multiple time zones. And if you have that many time zones, there is a good chance you have sun coming up somewhere and setting somewhere else. And it has so much offset that you have power and you have wind. And you can have some biomass. You can be sorted without even storage, but most countries do not have that luxury. So energy storage need to act as a buffer between intermediate supply and intermediate demand. So this is a coal power plant. Now, what does coal power plant do? It's a throttle valve. So your demand goes up, throttle goes up. You can match it. Okay, it starts to go down, you throttle it down. That's literally how it works. That's what power dispatcher does, and that's automated at this point in time. But you get the point. This is what's happening. It's like, oh, load went up. You do not think about it. Power plant is like, I got you, fam. More steam, more power. Got it. How do we get that? It's inertia. How does inertia work here? Inertia is law of physics that if a spinning thing is spinning, especially if it's a big ass heavy thing like a steam turbine that could be 100 tons to hundreds of tons connected to a giant shaft spinning at a very high RPM of 1500 RPM, or some are even higher RPM than that, but let's say 1500 RPM, you reach a point where it's like, okay, what happens? Somebody turn a furnace, a metal melting furnace, 10 megawatt, go. So what happens to that 10 megawatt? That 10 megawatt is leached from the transformer of that substation. That transformer now leaches it from the basically another substation. It leaches. You keep leaching away the magnetic energy. Where does it go at the other end? It goes to the generator that is producing it. Okay, it tries to do that. Now what happens? It slows down, right? Again, you are leaching energy. Energy cannot be created, not destroyed. So it tries to slow it down. Now here's the inertia acts as a buffer. It cannot eliminate it. There is no free energy there, but it takes time to slow down. Now RPM monitor would be like, RPM is 1500. Everything is good. Everything is fine. Hey, RPM is now 1499. 1490. Okay. Red alert. Again, it's happening hundreds of times a second. So it's like, okay, RPM is now 1490. 1480. Okay, increase steam pressure. So that spike, instead of happening like this, it's like, ooh. And again, this is happening inside a second, but it's enough for computer to be like, hey, I got this. Increase the steam pressure. That's how we do it. And again, same happens in reverse. You melt on your metal, so to say, and you turn it off. Boom, 10 megawatt gone. Now again, so much steam, so much spinning power. Now it tries to spin faster, but here's the deal. You still have hundreds of tons of inertia. That is like, 1500 RPM is like 1501, 1505, 1510. Okay, red alert. Okay, cut down steam. So that buffer allows our grid to survive. And each of these generators are in what we call synchronous mode, meaning they are synced. Every single generator in every country is synced to each other. So we have a ginormous mass, and that's how grid remains stable. Yeah, solar does not have that. So that's a very serious issue. So our grid safety is directly proportional to that mass being like, I got this. That's why when you have a substation fault, it gets limited to that. It does not do what we call cascade failure, because again, mass is like, hey, okay. You disconnected 250 megawatt, I got this. If you do not have enough mass, you don't got this. That happened in 2022 in America, where one solar farm and other substations like solar farms, and boom, 250 megawatt to 2 gigawatt went poof. Because there was no inertia to like, hey, I got this. So be mindful. There is inverter that is what we call grid generation, and other are grid following. Most inverters are grid following, and you want them to be grid following. But where does grid come from? It comes from that spinning mass. If there is not enough spinning mass, again, you can have like one generator that is 600 megawatt. That's not that much. You need almost half of what you are consuming. So even if in tomorrow you have like 10 gigawatts of solar, you want at least 5 gigawatts of spinning inertia. Not the actual generation, but inertia you need. And again, even 5 would be cutting too close. Again, for bad days. For good days, you do not even notice. For bad days, you do notice. So what can we do? What India can do? India has around 150 working, more than that, 150 working coal power plants. So coal power plants are super easy to convert into thermal energy storage, where you take the coal power plant, you heat the coal furnace and coal part of it, you heat the coal part and you replace it with this puppy, E2S. Yesterday I made a video about it in Science Thursday. It basically has a graphite block as a thermal block, and you dump energy during surplus, and you extract energy out of it during when you need to discharge it. So charging and discharging, and it works copy paste. Basically, you control C this and control V it instead of coal furnaces. Everything remains the same. Now you have that spinning mass, and even during daytime you will keep running it, because solar farms do not have their inherent inertia. You can have grid inverters that are made for this, but that's like still nowhere as good as like just spinning mass. Again, we're trying everything, like people are trying to make inverters that are like, whose sole job is to be the master inverter, so to say, but still risky. And be mindful, it's black box. When you're talking about mass, you know what you're talking about. And if it has an issue, you're like, okay, let's add more mass to it. Like some companies are trying to add same coal power plant generator. They're like, what if we add flywheel? If its inertia is not an issue, the rotor itself is few tons. It's like, I got this. It can stabilize light loads. If you have a flywheel that is like, 100 tons, like, I really got this. So coal power plants, we can get basically repurposing or coal power plants is super easy. And there are many coal power plants that are being deprecated for a few reasons. First could be pollution. Another could be running out of water. Again, thankfully, India has finally progressed to air condenser units. So this is India's first North Karanpura super thermal power project. Yes, it's super thermal because it's super critical steam. And it has air condenser. Thankfully, in India, we do not have too much fresh water, so wasting fresh water using cooling towers is unwise. That's a good solution. So you no longer have to worry about water. You no longer have to worry about coal pollution. And you get inertia. You get that oomph that can handle, a unit malfunctioning, a substation going offline, and have the inertia, like what we call a run through. Like basically, you had a fault, how easily you can ride through that. That will be exactly how it was. Exactly how it was. We are like, we still have it. It's just instead of coal, it's coming from graphite and not burning graphite. So that's a very good technology, and it reuses assets. So it's not like, oh, hundreds of millions of dollars that Australia is pouring into it. It's like it gives you grid inertia, because again, no matter how much battery you talk about, no matter what generation technology, mass is mass. It's like, bro, I got this. And storage. So we have the same asset, and we are like, okay, no more pollution, no more water loss. Again, we do have to add air condenser into it, but voila, an exact same power rating as it was. But again, duration would be up to us. If like, hey, we only need like 1 or 2 hour of buffer, small block. Like, hey, we do like to have buffer for a month, big block. Now, is there anything better? Because poor round trip efficiency is a big issue. If you dump 1 gigawatt, you'd be lucky to get 250 megawatt out of it. Now, you should get more than that, but you get the point. You are looking at 1/4 of return. But again, if you do not buy the power at that point in time when it's surplus, there is no power. It's off. There is loss. So you can buy power for very cheap, still making some profit, and you're still buying it. And during that evening peak time, lot of money can be made. And again, that's why peaker power plants are invented. Peaker power plants sell power at much higher rate than coal power plant, base load power plants. Base load power plants, let's say, has X. Peaker plant could be as high as 20x. Now, like, wait a minute. My bill does not reflect that. Yeah, your bill is being managed by people in power dispatchers. It's their job to make sure that your bill does not reflect it. And again, it's rounded off to unit size, power purchase agreement and all that. It's happening on a different level. That's why you do not notice it. So you have, at that point in time, if there is enough variability, let's say there is 5x price difference between the surplus duration and during peak demand, and meanwhile peak demand will always be high and surplus will always be cheap. It's just how much. And be mindful, I think it will be very, very competitive at that point in time. So even if you are buying a lot of energy, but you are buying it cheaply and you are only returning a small amount, still profitable, economically viable. And you also add inertia to the grid, so solar farm can survive. Pumped hydro storage is even better, but it has too much red tape. I'm seeing Israel is making a closed loop, which I always want. Like, you never want to touch rivers. You always want to be in closed loop. Or what Japan did try to do for some duration, for some decades, is like directly trying to run with sea. Can you do it with sea? Yes, you can. It's just that you have to handle the corrosion aspect and the barnacles, basically biofouling. If you can manage those things, you can utilize seawater for pumped hydro and then never have to worry about it. So that's a very good option, but it has too much red tape, like too much red tape. So I'm like, if I have to bet money, I'll bet money on coal power plants being turned into basically inertia and battery rather than pumped hydro. But we have the technology. Nothing new, nothing whoa. And this is like a technology readiness level 7. You need 9 is like pick up a phone and call. So we have already reached almost ready. Pumped hydro has been running from 1977. So everything is done. We have the technology. Interconnect and energy storage on a grid scale is compulsory. Now we come to the most critical aspect, economics, physics, engineering, economics. Now, economics is that, thankfully, I have noticed this, that most of the nations, and including India, they are learning for a fact that you are not actually independent if your fuel is coming from somewhere else. Meaning India could be like, hey, we are 75 years old and like we are independent and all that. And OPEC is like, oh, really? Our fuel goes offline and it's like, sir, what are you doing? Come on, man, brother. It's like, that's a bad situation. And again, even America had this issue with OPEC during oil embargo, whereas like OPEC is like, nope, and America went poof. So yes, even though you could be independent, you are not really independent. And triggering a war for oil is unwise. It's like wasteful. Now, so we realized very young, without energy independence, you're not truly independent, and independence is priceless. Plus, we need cheap and abundant power. For some reason, nuclear people do not understand it. Only people who like nuclear is people who think it's free or cheap. It's not. We have 100 years, or not actually 100 years, but you get the point. We have enough experience to know that it does not work. Like economically, it does not work. We need cheap and abundant power. Not only we need gigawatts of power, we also need it to be cheap. Gigawatt of nuclear is expensive, very expensive. Gigawatts of solar is like, bruh, take it and go. By the time you actually complete the plant production, that's in contrast. And that's assuming that nuclear actually gets done on time, which it will never be done. There is not even a single plant that is done on time, be it South Korea, be it whatever else. Solar plant would be built. It will have ROI, it will complete the ROI, and then it will be in profiting. So it's not viable anymore. And again, that was not there in 70s. That's why people were so optimistic back then. Now we are like, yeah, that's not viable. Like, think from a government point of view. You spent $1 billion to get 1 gigawatt of nuclear that might work 8 years from now, or invest 8 years later, you have like a power plant that is providing electricity. World has changed. And we need bonkers amount of it, hundreds of gigawatt. So abundant power is needed. Only then you can reach the growth target. Every nation needs it. We need bonkersly large amount of power, and it has to be cheap. Only solar and wind and some other renewables can do that. Because again, fossil fuel cannot do that. And fossil fuel price will always go up. This is one thing that is the most saddest part about American history, is that there was a time where they were smart. They had oil embargo. It was a bitch slap to them, and they were like, okay, we're going to use our brain. They used to have it. So the brain was, what if we created a solution to this problem, where instead of relying on other countries, we got our own source. They did a project called Project Aquamarine project, and you can download the PDFs online. It's available. So the project was started in oil embargo, cancelled in 1999 or 1996, somewhere in 90s. Basically, it was cancelled, and the result was nothing can be grown on land that will provide enough to satiate our fuel needs. That's not gonna happen. Law of physics is like, bro, the yields are not high enough where you can like, oh, we have, and if population growth happen, you're gonna have food shortage. So, or like food price will go up, because again, farmer will have fuel crops and food crops. You never want that. You never want fuel crops ever to be planted. Any country that tried this stupidity, be it Brazil, be it America, or be it India, the food prices slowly started to went up, even though that should go down in price. We are improving the technology, we are improving the yield. Why the price is going up? Because again, now you have competition. Like in India, we are smoking ethanol weed. So it's like, what if we had sugar? It's like, we need rice, we need potato, we need tomato. We do not need sugar cane, more top of sugar cane with some extra sugar cane. And Brazil is like, what if we had extra sugar cane? And again, America is like, what if we had corn with some even more corn? And it's like, why the food is going more expensive? So you cannot grow anything enough. Basically, you cannot grow enough. There's only one possible option was basically algae biofuel. But again, algae grows on a pond. So you can do that in a desert without compromising land of a farmer. Then it's like, why don't we do that? Yeah, fresh water. It requires 700 liter plus per liter of petrol or per liter of diesel. Yeah, you do not have enough fresh water on the planet. You do not. You just do not have that much fresh water. And be mindful, human consume it. So first priority is this puppy. So what was the solution? Solution was seaweed biofuel. Why? You need ginormous surface area. What has ginormous surface area? Sea. What has ginormous amount of water? Sea. What does it have? Salt. So normal things will not work. So you need seaweed biofuel. That was the only, it has lower yield than compared to algae, but scalability. Basically how solar can scale, it can scale too. But they closed the project because at that time in time, OPEC, somebody was smart in OPEC. They were like, okay, these people are close to actually using their brain. Let's drop the oil prices. It went below what it was during oil embargo, a lot below. And they were like $15 per barrel. And the scientists in the project were like, the best we can give you is 2x the price, meaning $30 per barrel. And this line everybody keeps parroting like a retard. It's like, oh, it's twice as expensive, which is factually true. It's just that twice as expensive from that time, not today. Not today. We are not buying oil for $60 per barrel. We are not even 60, 30. So if we kept pushing at that point, or they were like, okay, just grow enough where we can refine the pipeline, just keep working at it, and that will have price locked OPEC. But they did not. That was the dumbest mistake ever done. And I am like so frustrated by everybody's like, what if we destroy the farming lands just so we can make oil? It's like you have sea, you have infinite surface area mathematically. But again, we have learned this the hard way. Same thing happened with solar. This is 2014, India, 3.7 gigawatt. That is a lot of energy. But again, if that point in time, which again, 2015, 14 is not that back ago, and you talk to someone, it's like, bro, India is going to have like almost 50 gigawatts of solar. People would have laughed at you. They're like, bro, what are you smoking? This is 2023 to 2024, 74, 20x. Let that be very clear. 20x growth in solar in 10 years. Happened, past tense, I'm not talking about future. And solar will keep growing like this. Unless, assuming the grid can handle it. If the grid cannot handle it, it will not grow. But this happened. And why solar can go down in price? It's not a limited resource. Even because of inflation, you're like, okay, the panel cannot be below a certain price, but the panel wattage can go up. You could have spent $100 for 100 watt panel. Then you can spend still $100, but now you get 250 watt panel. You can still spend $100. Now you can get 500 watt panel. And we are still at single junction solar panel. We know the science. Science is like, bro, go multi-junction, go, instead of limiting yourself to 20% efficiency, yeet to 40% efficiency. We have the science. Science is tested. We are using it on satellites. We're good. We sorted. It's just mass production is not there. Because again, demand is not that much. But we can. There is so much scope. Oil will have a limited amount of oil. It will run out. It will go higher in price. So that OPEC price reduction, that was awesome. They killed the project and now everybody's addicted to it and everybody's running like a retard, going back and forth, back and forth, back and forth. It's like, nothing will work. And I've seen somebody like, what if we did jatropha planting? I'm like, see the yield, man, per hectare yield before opening your mouth. So fundamentally, renewables will keep going down in price. Again, India, same happened in China. So renewables will keep going down in prices, but it will only be true if we can absorb the power. If, let's say, this happened. Now, let's say double it. Again, reasonable to say. Let's say you double it by 2025, let's just say. Okay. But let's say during peak time, everybody had to shut off because, again, distributed power. You do not have enough interconnect where you cannot dump it. You do not have enough energy storage where you can absorb it. What happens then? Now people stop installing it. People stop building solar farms. People stop building wind farms because they are not getting ROI. And then this tapers off. You do not want that. So round the clock power, meaning 24 into 7 into 365 power, it's expensive. Now, thankfully, we do not need any new technology to do that. Everything I have talked about already exists in India or is in trial stage. It's there. We got it. We are sorted. Heck, we are the first to have multi-junction, multi-port HVDC. We got it. We are sorted. We just need a giant loop of it to connect multiples of it. It's there. Market is ready. Market is not like, okay, what if you invest this, and the market is ready. Just ready to go. You just need to expand the grid so they can place where nature wants it to be placed. Market is ready. Grid has to be ready. Energy storage has to be ready, and then problem sorted, because then you can have abundant power, because again, solar is free during curtailment, and wind, again, free during curtailment, and you can just absorb it and sell it just a bit more price. And just to justify the investment of that, energy storage system. And how can India afford to do this? That's a very good question. It's like, yeah, that's a good thing. We want more grid. We want more energy storage. That's good. How would we pay for it? Electricity theft. The primary failure, the reason why India did not become the god power that it could have become, is because we do not throttle this electricity theft. Different states have different levels of it. Some states are okay, some states are sorted. Like Gujarat is sorted, meaning when I was in Gujarat, it was shocking to me that there was no power cut. When I went as an adult, it was even more shocking that there was no inverter shop. Every state that I visit, other than that, has inverter shop. Every basically block has an inverter shop. Inverter shop is basically a battery unit which just act like a generator for us. Like, we are so used to power cuts that we have the setup to solve it, because if power cut happens, many times you will not know that power cut has happened, because again, all our electronics will keep working because of the inverter. It's almost like a UPS for home. Think in that way. We are used to that. Every state has that. And Gujarat is like, nobody even buys it. It's like, somebody may buy it like a dual conversion online UPS for ATMs or for medical equipments, but nobody else bothers with it. So fundamentally, you have to stop electricity theft. If failure to do so, you have basically what we call loss. The loss piles up and then it becomes national debt. Like some states, they do not have to worry about it. Other states, 30,000 crore rupees debt. Now here's the deal, you're like, that's a rupees, how much is that? Yeah, even if I remove the zeros from it, like 2 zeros, just to give buffer, yeah, still is a lot. Even in dollars, it's billions of dollars of debt. This is one thing that China really sorted it out. It's like, if you're poor, you do not justify, you do not get to justify electricity theft. And this is what messed up South Africa. South Africa was going very high up, then they messed up the electronics. Electricity theft is a very brutal failure. Like, we really have to sort it out. And if we sort it out, we have more than enough money. It's like, money is like, bro, we sorted, we tight, we good, we done. We done, we good, we are going. We just need to sort this part out. So then we can be like, we're really good. Like 24/7 into 365, cheap and abundant power. We good. We can do it, but we have to stop that part. And thankfully, economics is working in positive direction, because again, coal is cheap today, not actually cheap. It has already crossed over, meaning in 2015, it was same price as solar. Now solar is cheaper. And again, with energy storage and better technology of energy storage, you will reach a point, especially with pumped hydro, you're like, bro, it's not even a competition at that point. And again, if coal prices go up 2x, 3x, it will reach a point where it's like, even with that 25%, 75% wastage charge of thermal energy storage still would be worth it. Like, we have reached that. And again, coal, gas, oil, these things prices are going constantly up. There is no competition there. It's like, it will always go up. Solar will go down, wind will go down, but other things will not. So economics is there. It's already, like, it's good for us to do, not for planet. It's good for us to do. So what can we expect in the future? Well, reality is we need a very good grid. Failure to do so, it will arrest our momentum. So India has built momentum, right? In last 10 years, we 20x'd our growth. That's good. That's like really good. But if we do not have the grid that to absorb it, and we reach a curtailment point, this will happen. This is what we call the duck curve. This is from California, very popular duck. And worst things would happen. First, progress will stall, so less people will be like, let's not build too much of it, and then it will be reversed. People will stop building it. That backfires. So how do you stop that? How do you stop loss of momentum? Well, first thing, never ever reach power curtailment. That's the first thing. This is a small example from a small country in Europe. I'll let you worry about it. They're putting a lot of wind, and they're like, bro, GG, awesome, we got wind. But here's the wind. In the early days was basically a turbine blade, that was like that wind blade, rotating at a sort of fixed RPM, but they had a blade pitch control to basically reduce the RPM or increase the RPM based on the wind speed. And the gearbox, so gearbox will take a high torque, low RPM and make it into, let's say, 1500 RPM for the generator. And it did its best. All the computer did its best to make sure the RPM remains locked. Now, was it possible? Yes, it was possible. It was acting as an inertia. So if turbine started to increase up, it gave enough oomph. The resistance from the generator was enough that it allowed a computer control to change the wind angle, basically the blade angle, so to say. And then it created an issue. It's like you are literally fighting two forces: inertia in that magnetic field and inertia of the wind, of that big ass mass. And gearbox was like boom. Gearbox used to went to boom almost every day. It was bad. Like, if you hear about like a wind turbine requires too much maintenance, that was the maintenance weak link. You literally was fighting between two forces, natural forces and grid inertia. It's like, and gearbox is like, brah. So then we upgraded the system. It's like, okay, RPM, go YOLO. basically the field current that is in the stator go whatever hertz you need to, like 50 hertz, 60 hertz or whatever, like there is a range. We allowed the range to be okay, awesome. Then how do you link it to the grid? Then we started to do what we call doubly fed induction motor. So idea was the rotor was now basically a generator, field generator, where we were providing counter current. If the RPM was too much, we provide, let's say instead of getting 50 hertz, you are getting 60, we provided counter rotation of 10 hertz to compensate for it. It's like, did we had to do that? Yeah. Now, why did we do this? This allowed a very small inverter. So let's say it's a 10 megawatt unit, not 10, let's say 5 megawatt unit. You only need few kilowatts of counter current to balance it out. So it was a small inverter and we got it. And again, gearbox started to last longer. And because of the development in solar, people looked at it and they took that gearbox, yeeted it, took that double effect induction generator, yeeted it, and just like, okay, put a BLDC motor there. And now it's completely fro. It's like directly rotating, directly getting power out of it. And what about the frequency? Now there is an inverter there. Consequence, there is no inertia. Now, inertia was lost the moment we had a electrically fed system, but still had some oomph to it. But now it's gone. It's completely free floating. So this European countries, like we are putting so much wind, we will lose inertia, and you do want at least 50% of your electricity from inertia. We are learning it the hard way, that we are like, what if we remove 100% of it? It's like, yeah, without inertia, you will be unstable. So they're like, they had a small coal power plant. They're like, okay, if you have coal power plant, what does coal power plant do? They have a generator. What is that generator? It's a synchronous motor. All generators are motor, or motors are generators. So that synchronous feature was the desirable feature. They're like, okay, yeet the turbine part of it, put a big ass flywheel there, like as heavy, as big as you can put it. They put it. Now what does this become? This becomes what we call synchronous condenser. So they run it like a motor, match the frequency of they need to, and then done. This puppy now not only provides you inertia, it also provides power factor correction. Controlling the rotor current, they can be like, okay, active power factor, negative power factor, they can control it. And because of the inertia, if let's say inverter tries to push higher, they're like, whoa, 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 whoa. Because here's the inverter are following. They do not generate their own waveform. They follow the waveform in the grid. There are certain inverters that are designed to be the master, but I do not trust them. And again, they are ludicrously expensive and very untested. This puppy is like, bro, I have been tested for 100 years. And again, ride-through capability of these things are awesome. So you have a surge, it's like, it can just like, it can handle the surge and it's like, got this. They're very good. And again, you can even have huge spinning mass. And like, wouldn't it consume power? Little bit. Once it is at the RPM, it does not change. It's not a load. Let that be the case. It's basically a synchronous motor without a load. There is no quote unquote load on it, no mechanical load. It's just a mass that is spinning, that is providing the inertia. Basically, the rotor, the stator that is creating the waveform, that waveform is the master waveform. And because it's magnetically coupled to a mechanical rotating mass, it has the inertia, absolute inertia. Basically, now every inverter in the system, all the basically wind turbine inverter is like, this is the master, follow this. So we solve that problem. Every problem can be solved. And we cannot allow power curtailment to happen. So ROI on renewables would become bad if that happens. And this is a problem. What is this problem? This is, if you take 12 a.m. to 12 a.m. of another day, you will find this curve. So sunrise happens in generally around 6:30 and sunsets are around 6:30. So solar panel starts to produce power. Okay. Now, why the heck this line is going down? This line is basically demand of California on national grid. So basically demand was very high, around 20-ish gigawatt. Okay, cool, awesome. And then solar panels started to produce power. Okay, started to drop. Then during evening, when people started to return and sun has set, the spike power happened, very expensive power at this point in time, and then normalized. So this duck curve. Now, duck curve has an issue once it starts to touch the bottom. Now, again, this only started to touch bottom in 2023. People were warning about this, but nobody was taking it seriously because in 2015 it's here, 2016 here, 2017 here, 2019 here, 2020 it's here, 2022 it's here. 2023 is really touching. It's actually pushing through. If you watch day by day, there are whole days where it was like, it was actually disabling the grid from around 11 to around 2 p.m. Like it was like turn it off, meaning it was overproducing so much they had to turn it off. You want this line to be zero, that means you are not buying in electricity. But here's the deal, we are reaching that point. You're like, what if we add more solar? You reach negative, you have to turn it off if you do not have energy storage, if you do not have interconnect. Ideally, if you have very good European structure where you like just interconnect everything, you're like, okay, just keep adding more solar. It's like, what happens when we go below this? right? Like, okay, now sell the power to other states. If Germany could have done that from their northern Germany to southern Germany, they will be chill. They will be like, bro, our electricity will be cheap. But they're like, yeah, they messed up. So a nation must stay ahead of this. Basically, this should not happen, because the moment this start to happen, I can guarantee you all the solar farm owner will like, but a dispatcher just disconnects us. Because again, they cannot disconnect household, they have to disconnect the solar farms, and solar farm are the main bulk profit, so to say, profit maker. And if they lose their profit, they're like, okay, let's not build more solar farm. You are stuck. Same happens with wind. So you must make sure this does not happen. Solar is very easy. That's why we have the duck curve. And again, even that coal power plant to energy storage, you can store so much power here. Just ride through this, wind will be take care of rest. Just ride through this. We only need 5 to 6 hours of ride through capacity, and then wind is like, we got this. And if you have boatload of wind, boatload of solar, then you can just keep storing as much power as you want for a few days. And again, you really have to go through really bad days, really bad weather, only then you will run out of energy. So a nation must stay ahead of it. Basically, 15, 16, 17, 18, 19, if this start to happens in your grid, make sure this never happens. This never happens. Like, this should not happen. So if we do not do that, the ROI goes away. And basically, thankfully, we have the technology. That's the good part. Technology, old, ancient technology. We have it. We used to have it. Before we had like a capacitor-based power factor correction, this was available in every shop. They had a motor running, and like again, rotor current was being arranged. So power factor was adjusted. Now we are going back to it. Mass, inertia. Oomph. So this is the future. We have the technology. Let that be very clear. It's like, oh, we cannot add the grid. We got it. We sorted. We learned through this. Like by 2020, we have a research article to research paper to incident report to everything we need in order to make a grid that's like, I got this, fam. We got it. We sorted. We just have to have the will to it, or balls for it. If we do, I can easily see India be like, in next 30 years, be like, bro, we sorted. We sorted. Energy is not an issue. We sorted. I can see that. So this was my presentation on how can we make sure that India's grid is ready for renewable transition and not create a fallback issue for ourselves. So hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me excess disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.